Hello, everyone, and welcome back to Nunley Math. I'm your host, Aaron Nunley. Thank you so much for joining us here today as we continue our unit on ratios, rates, unit rates, and proportions. This is the third or fourth in our series of videos on that particular topic. Today, we're going to look specifically at rates of change. Rates of change. So let's just go ahead and hop right in today. When we talk about a rate, you will remember that a rate is a comparison between two unlike units. For example, in this table, we're talking about a comparison between meters and seconds. And you can see this table gives us several examples of meters and seconds. We go 0 meters in 0 seconds, 20 meters in 3 seconds, 40 meters in 6, 60 in 9, and 80 in 12. And we talked about how we can take a look at each of these individual rates, and we can use division to write these as unit rates. So if I go 20 meters in 3 seconds, I could actually divide that out and come up with a unit rate of, I believe, 6 2/3 meters per second, and I could go through and do that for each of these ratios. We also, in our last video, talked about the fact that we could use one of several methods to determine if this set of ratios or rates is also proportional. So we'd set up each of these ratios as fractions, and then we could either put them in simplest form, find common denominators, write them as decimals, use the mean its extremes property, or find a constant of variation. There again, that's a quick review of the last couple of videos, but that is not what we're looking at today, because today we're not just looking at rates, but we're looking at rates of change. Rates of change. In other words, we're not just comparing meters and seconds. A rate of change is a comparison between how two different units or two different items are changing at the same time. And if you have this written down, you might want to circle or underline or highlight or star that word right there. How the two different items are changing at the same time. Because I'm no longer comparing just meters to seconds. I'm comparing how the meters are changing compared to how time is changing. And you'll notice I wrote that as a rate using words and using my division bar. A lot of times in math, we don't like to spend a lot of time writing out these long words. So instead of using the word change in, we'll sometimes use a little triangle here. This is actually the Greek letter delta or the Greek letter D, and that is often used to represent the change in an item. So this is a shortcut way of writing change in meters and change in time. So let's take a look at what that looks like. If I want to talk about the change in meters, what I want to see is that in my first two ratios, or rates, I apologize, I've gone from 0 meters to 20 meters for a change of 20. I've gained 20 meters. But it took me 3 seconds to make that change in distance. So I have traveled 20 minus 0, or 20, meters in 3 minus 0 seconds. Notice I can write that out. If I take my ending distance minus my initial or starting distance, and I divide it by my ending time minus my starting time, that's going to give me a change of 20 meters in 3 seconds. Notice I'm not just taking any one of these rates and converting it to a unit rate. Instead, I'm looking at how we change over time. Let's look at the second set of ratios, or rates, I apologize. I've gone from 20 meters, or a distance of 20 meters, to a distance of 40 meters. That's also a change of 20 meters. And I went from being 3 seconds into my timing to 6 seconds into my timing, which is also a change of 3. Or, if I wanted to write that out as a subtraction problem, I take my ending distance, 40, minus my starting distance of 20, which shows that I changed 20 meters. Then I take my ending time, which was at 6 seconds, minus my starting time, or when I started timing this distance, which was at 3 seconds, which is a change of 3 seconds. Notice that my distance and my time are changing at a rate of 20 meters in 3 seconds. That was the same as with this first example. You might want to pause the video and go ahead and calculate this third pair on your own. I'm going to assume you've already done that if you wanted to, and I'm going to keep going. We go from 40 meters to 60 meters. We go from 6 seconds to 9 seconds. In other words, I ended at 60 and started at 40. That's a change of 20 meters in 9 minus 6, or 3 seconds. Again, that was the same. The last example, I'm going to go ahead and speed through just a little bit. I'm going to show you that it's the same as well. We're always moving at a rate of 20 meters in 3 seconds. And we can always calculate that by subtracting our ending points minus our starting points. Now, in this particular example, our rate of change was constant, but that is not always going to be the case, as we'll see in some further examples. By the way, if you want to put that as a unit rate, and I do recommend that you do that, 20 divided by 3 is going to be 6 2/3 meters per second. Meters per second is a derived measure or a speed that's obtained by dividing distance and time. Here's another example for you. The table below shows the weight of a dog in pounds between 4 and 12 months old. Use the information in the table to find the rate of change in the dog's weight between 4 and 8 months, and also for 8 and 12 months of age. This is an example I grabbed out of an old textbook. Notice that our rate is comparing age and weight, or months and pounds. When I write this as a ratio or a rate, though, what I want to do is I want to make sure that my rate has the time on bottom. Remember, this could be a rate of 4 months for 15 pounds, but it's more common to put time on bottom, or 15 pounds over 4 months. So we're talking about the change in weight compared to the change in age, which there again I can write as a shortcut. We want to make sure that we put our weights on top and our time measurement on bottom. Well, let's see. The age goes from 4 months to 8 months. The weight goes from 15 pounds to 28 pounds. Notice that that is a change of 4 months and a change of 13 pounds. In my class, I would have my students write out that subtraction problem. That habit is a really good one to get into and is useful for us further on down the road. So 28 pounds is my ending weight. We started at 15. That is my gain of 13. I stopped measuring at 8 months. I started measuring at 4 months. That is a change of 4 months. So the puppy has gained 13 pounds in 4 months, which then I would go ahead and write as a unit rate using division. 13 pounds divided by 4 months is 3 1/4 pounds per month. That's 13 divided by 4. Notice that the question does go on to say between 8 and 12 months, they'd like us to get that rate of change as well. So I'm going to go ahead and do the same thing for this second pair. Again, I'm going to recommend you pause and try this portion on your own and then restart the video to see if you're getting what I'm getting. The age went from 8 months to 12 months. The weight went from 28 pounds to 43 pounds. Since we're putting weight on top and time on bottom, I'm going to do 43 minus 28. That's my weight change. 12 minus 8 is my age change, for a change of 15 pounds in 4 months. Or as a unit rate, 15 divided by 4 is 3 3/4 pounds per month. Notice that in unit rate form, we can compare and see that the amount of weight the puppy gained between 4 and 8 months is less than the puppy gained between 8 and 12 months. This is not a constant rate of change. Again, here's a problem I grabbed out of an old textbook. What I'm going to recommend to you is that you pause the video, you try this one on your own, and then you watch the video to see if what you're doing matches what I'm doing. If you feel pretty confident in your answer, you can use your fast forward button to skip to the end of my explanation. If you're still uncomfortable, certainly you can watch it as I talk my way through it. The table below shows Julia's height in inches between ages 6 and 11. Find the rate of change in her height between the ages of 6 and 9. Now, it's important to note here, the question only asks us about the ages 6 and 9. It does not ask us about the change between 9 and 11. Certainly, we could calculate that, but it is not required of us, so I'm not going to bother doing it. It's just extra work. In this comparison, you will notice that we have the age in years, the height in inches. As a general rule, it's a good idea to always put time measurements on the bottom. And here it is written as a shortcut, delta height over delta age, change in height over change in age. Notice that between 6 and 9 years, that's a gain of 3 years. Between 52 and 58 inches is a gain of 6 inches. 58 minus 52 over 9 minus 6. We always subtract the ending point minus the starting point. You get 6 inches in 3 years, which is 2 inches per year. I did just notice a little bit of a typo here. We don't subtract the ending point from the starting point. We do the ending point minus the starting point. Little grammatical issue there. We want the ending point to be first. A good thing to note is that if we had done the starting point minus the ending point, if we were to switch these and switch the bottom, we would get -6 over -3, which is also 2 inches per year. But what you're basically saying here is that we lose 6 inches if we go backwards 3 years in time. And we'd still end up with a +2. The reason I tell my students to always do ending minus start is more often than not, it's going to help you eliminate some of the issues here with the negative signs. Also, if you start doing ending minus start, but then on the bottom you do start minus end, and you start switching the order of those things, you could end up with negative answers when you really shouldn't. So try and find a way to be consistent about that. Saying ending minus start is my way of making sure that I do that. Let's keep going. Here we have the same information or same type of information given to us in graphical form. It says the graph shows the size of the seal population at seal point for the years 2008 to 2013. Find the rate of change in population each year. Oh, I don't like that because each year means I need to do it between every pair of points in the graph. That means I'm going to have 1 rate of change, 2 rates of change, 3, 4. There's going to be 5 answers to this short little question. Watch out for that word each. It does sneak up on you just a little bit. And then lastly, we're asked to find the average rate of change of the population for the entire span. So we'll do that in a second. I'm going to go ahead and do the first one for you. Then I'm going to ask that you pause the video and try the rest on your own. I'm looking at the change in population as time passes. Notice that the population here is on the y-axis and time is on the x-axis. We often put time on the x-axis. That's actually a very common way to do it. So when I set this up, change in population over change in time, I'm going to be examining how much the graph goes up compared to how much it goes over. And notice that I've written this as delta x and delta y being change in population, delta x being change in time, because the population is on that y-axis and the time is on that x-axis. So from 2008 to 2009, if I'm looking at the change in the population, this says that we went from 25 seal up to, let's see, this is at 40 seal. We have an increase or a rise from 25 to 40. That is an increase of 15 seal between 2008 and 2009. That's 1 year. So if I wanted to write that out, 40 minus 25 over 2009 minus 2008 is a growth of 15 seal in 1 year, or 15 seal per year. What I would recommend to you is that you pause the video and that you work out on your own between these second 2 years. Remember, when you're talking about the change in population, you're asking, how high did I go from here down to here? Always moving left to right. And when you talk about the change in years, you're going from here to here, that left to right. I'm going to assume that if you wanted to do that, you already did. From 2009 to 2010, we went from 40 seal down to 35. So we always do our ending minus our start. And that's going to be 35 minus 40. And then for time, it's 2010 minus 2009. That is a decrease of 5 seal per year during that 1 year span. Notice, because my population went down, I got a negative answer. I always make sure I do end minus start so that I don't get confused about my negative signs. If I had switched these on top and switched them on bottom, I would have got positive 5 seal and negative 1 year, which is also negative 5 seal per year. The third one, from 2010 to 2011, you went from 35 to 30, 35 to 30. That is going to be a decrease of 5 seal. Our ending was 30, our start was 35. So we went down 5 seal per year. Again, you've tried the next one on your own. We have gone from, let's see, 30 seal up to 35 seal. That's going to be an increase of 5 seal per year. And then the last one that you've already tried on your own, we go from 35 seal up to 45. So when I subtract that, that is an increase of 10 seal in 1 year for 10 seal per year. How'd you do on that? Did that make sense? The computation portion of this is not real hard. It's also nice that our denominators are gaining 1 every single time. That makes the turning to a unit rate at the end very easy. That will not always be the case, so you do want to watch out for that. For my students in my class, the first couple of days I make them write out all of this because I think this is a good habit to get into. But as we get further and further into this unit, I will allow them to just look here and draw arrows and count, especially since it's always gaining 1. So I would just look here and say 15 seal 1 year, negative 5 seal 1 year, negative 5 seal. And I would allow them to do that eventually, but not here on this first day. Last thing we need to make sure we talk about is this average rate of change of the population throughout the entire span. When we talk about the average rate of change, we're saying if we just look at the initial starting value and the ending value, ignoring all the little changes that take place in between. From 2008 to 2013, we started at 25 and ended at 45. That's an increase of 20 seal. And we started in 2008 and ended in 2013. That is a difference of 5 years. We've gained 20 seal in 5 years, or an average of 4 seal per year. When we talk about the average rate of change, what we're basically doing is we're saying if we were to draw a smooth line all the way across, a straight line all the way across, and we're to ignore the year-to-year changes, there's always going to be some small variation from time to time. You can't predict there's going to be exactly a growth of 4, exactly a growth of 4, but what's going to happen is you're going to have big growth some year and small declines the other. But if you look at this as a whole, this appears to be the general trend. So we are seemingly gaining 4 seal every year. Does that make sense? Hopefully it does. That is the end of this video lesson. I'm going to go ahead and pop back to this slide. Hopefully that has made sense for you. Again, the thing that people struggle the most with when they're doing these kinds of problems is making sure that they get their subtraction in the right order, so they get positive values when they should and negative values when they shouldn't. So just be very, very conscientious about that. The other spot that my students tend to struggle is they also tend to leave off their units here on the end. So make sure you're including your units on all of your rate problems. As always, I do appreciate you joining us here today. I do thank you for your attention. I wish you all the very, very best of luck. You all take care of yourselves, all right? Bye-bye.